ask Elon Musk, he will say, yes, indeed, we do live in a simulation. And the reason is because he believes that there's three possible outcomes for the future of humanity. The first one, we go extinct and kill ourselves. Second, we survive, but we are not interested in running any simulations. And the last one, we are interested. And according to him, the last one is the most probable, and therefore we're probably in a simulation. But you may be wondering, can you run a simulation so complex, like reality? Well, I may have the answer, which is quantum computing. Now, before we actually start talking about quantum computing, I'd like to give you guys a brief overview of the state of our classical computers. So now this is Moore's law, and basically it states that every 2 years the number of transistors on a semi-chip would double, and this actually holds fairly accurate until very recent years where we started experiencing some slowdowns. Now this actually suggests that there may be a hardware limit that we may reach at some point to classical computers. And why is that? Now here's a picture of a modern transistor. So you can see it's just like a few hundred nanometers in size. So just to put that in perspective, if you put about 1,000 of these in a row, the length you would obtain is about the exact same as the diameter of a strand of your hair. Now that's really, really small. And at this length is when things like quantum mechanics come into play. Now one thing that really impacts us a lot is what's known as quantum tunneling. And quantum tunneling basically means that electrons can actually surpass or tunnel through very thin barriers, which would render a resistor or transistor completely useless. This means that there's some things that computers will never be able to solve, like for example, optimization and simulation problems. And a specific example for, let's say, an optimization problem would, let's say you want to go from one city to another city by car, and what is the most optimal route you can take? So there's many, many factors you would have to consider. Each individual route that you can take, the time of the day, the weather, the human, the traffic, and a normal computer would take a long time because we have to analyze each individual case individually. But a quantum computer can actually run these calculations in parallel, so it would only virtually take one step if you have a powerful enough quantum computer. And the phrase quantum computer is coined by this man right here, Richard Feynman, who said that the only way we can simulate the quantum world that we live in is through a quantum computer. And compared to a normal computer, quantum computers can perform many calculations in parallel, and they're also able to scale exponentially. Now, how does the quantum computer actually work? Well, quantum computers are made of qubits, which are quantum bits and can be in a state of 0, 1, or a superposition of both. And superposition, simply put, is what allows qubits to be in both states because it can be represented by a probability of it being a 0 or 1 when you actually measure it. So like here, when you have a classical bit that can only be two distinct points, a 1 or a 0, a qubit can be represented more like the surface of a sphere, where you can select any value on there. And another property that is really important is what's known as quantum entanglement. And that basically allows multiple qubits to communicate with each other. Now with these two principles, this means that if we have one qubit, we're able to simulate two states at the same time. If we have two, it'll be 4. So every time you actually add a qubit into a system and entangle them, you will actually double the computing power of the quantum computer. Now there's many ways of actually making a quantum computer, and today we'll talk about a very specific case, which is D-Wave. Now D-Wave was started in Vancouver right here by 2 faculty members of UBC, and it's one of the only private quantum computing companies in the entire world. This is their newest model, the D-Wave 2000Q, that sells for about 15 million. So you can probably buy one if you have enough money. So the 2000Q, why is it called 2000Q? So 2000 means that it has 2000 qubits. Now this doesn't mean that it can simulate 2 to the 2000 states at the same time, because that would be just absolutely insane. And because this is why D-Wave is quite controversial in the field, because D-Wave's qubits are actually they're very noisy. So each measurement you would get or reading from each individual qubit would have a lot of error in it. But D-Wave's approach is they go for quantity over quality. So they believe that if we have a lot of noisy qubits and noisy measurements and we combine them, we would achieve an accurate answer. And that's still debatable. Well, let's actually go into this quantum computer. What does it look like? Now this is the inside. As you can see, it's surrounded by a metal housing. Now this metal shielding is what shields the inside of the quantum chip from the outside radiation and electromagnetic waves. And then this here is, right there, is a dilution refrigerator. And dilution refrigerator basically cools the actual chip down. So each individual level here cools the chip down all the way down to like 0.02 Kelvin, which is like one of the coldest temperatures that's ever achieved. And the chip just rests at the very bottom, which is pictured on the right. And it's about the size of your fingernail. So why are we doing all of this? To cool it down and shield it from all that radiation? It's because of what's known as quantum decoherence. Now, quantum decoherence basically means that quantum information cannot really be stored for long because there's a lot of noise and interference from the environment. So anything from disturbance can cause a huge error in the system. Now, here's two like random pictures I found on the internet, and I found this pretty interesting. So here's a computer in like the 1940s, and beside that is IBM's like quantum computer now. So you can see that there's like a large resemblance between these two pictures. Because in the first one, and both of them actually, they all take an entire team of trained scientists to operate, and they take up an entire room. This means that like right now, we're in a very initial phase of the development of quantum computers, and there's still a lot to be discovered and to be learned from this. But quantum computers are not really a replacement for our modern computers, but rather it's more like a specialized tool that is used to solve certain problems, like a GPU would be in your laptop. Now, modern problems require modern solutions, and quantum computers can solve a lot of our problems. Thank you.
How do you think quantum computers will affect cryptography, for example?
So in terms of like cryptography, right? So there's a lot of concerns regarding like quantum computing and how it can destroy cryptography. Well, that's true on like modern cryptography, like the way that it's built, because of the parallelism, it can simulate, like, it can go through multiple calculations in parallel, right? So it would break that. But there's also like theories and things that people have come up with that use like quantum computers to make like quantum like keys kind of, which then would make it impossible to solve with the quantum computer. You have to come up with something else. Yep.
How would software work on a quantum computer?
Okay, so right now, this is why like quantum computers can't really be independent of normal computers and can't replace them, because right now, like for example, the D-Wave computer, how you actually communicate with it is you take a classical computer, you write some like code, right, and it sends it to the quantum computer, and they use like microwaves to actually change the state of each individual qubit, right? So you still need a classical computer, and you have to write code on there, not directly to the quantum computer.
All right, thank you.